Imagine, just for a moment, a world where the artificial intelligence you interact with daily, the chatbots, the recommendation engines, the image generators, are not just getting smarter, but are undergoing a radical transformation powered by something that sounds straight out of science fiction, something that promises to break free from the chains of traditional computing power that have held AI back. For years, the realm of artificial intelligence has been absolutely ablaze with progress. We've seen models grow exponentially, processing unimaginable amounts of data, generating text and images with startling creativity, and even helping us solve complex problems. It feels like we're living in a golden age of AI discovery, doesn't it? But behind the scenes, there's been a growing whisper, a question that haunts the developers pushing these boundaries. How do we keep this incredible momentum going? Because the reality is, the fuel for this AI fire, the sheer computing power required, is becoming increasingly expensive, energy-hungry, and frankly, constrained by the very physics of our current technology. We're talking about data centers the size of football fields, gobbling up electricity equivalent to a small city, just to train these colossal models. And for the longest time, quantum computing, that mysterious field dealing with subatomic particles and strange physics, felt like a distant dream, a futuristic tool destined for niche scientific problems, maybe decades down the line. The two worlds, AI and quantum computing, seemed like ships passing in the night. But sometimes, two seemingly separate rivers converge, creating a powerful new current. And that moment, my friends, has just arrived. Picture this: a research team, tucked away in China, at a company called Origin Quantum, a name that itself sounds like it belongs in a sci-fi novel. They recently announced a groundbreaking achievement, something that has sent ripples of excitement through both the AI and quantum communities. They successfully fine-tuned a large language model. Think of it as optimizing and sharpening an existing AI brain. A model with a staggering 1 billion parameters. Those are essentially the knobs and dials that make the AI work, using a quantum computer. Now, 1 billion parameters might not sound huge compared to the models with trillions of parameters you hear about, but successfully manipulating any model of that size on a quantum computer is a monumental task. And the results they reported? Truly remarkable. By leveraging the unique capabilities of their quantum machine, they achieved a 76% reduction in the effective number of parameters needed for this fine-tuning process. Think about that for a second. It's like taking a massively complex machine and figuring out how to get the job done using less than a quarter of its moving parts. And here's the kicker. This wasn't just about making it smaller. They reported that this quantum-assisted process increased the training effectiveness by 8.4%. More effective training with drastically fewer parameters used on the quantum side. This isn't just a cool experiment. It's a global first. It marks a truly significant milestone, a tangible point where the bleeding edge of quantum computing meets the explosive world of artificial intelligence in a way that produced a concrete, measurable result. It's like the first time someone successfully used a specialized formula from advanced physics to build a more efficient engine for a car we all drive. So, who is this Origin Quantum? Are they just some ivory tower researchers? Not at all. Origin Quantum is a technology transfer platform affiliated with the prestigious Chinese Academy of Sciences. They aren't just dreaming up quantum computers, they're building them. They've engineered multiple generations of these incredibly complex devices, exploring different foundational technologies like semiconductors and superconducting circuits, and they're not just building them for show. Among their fleet is a superconducting quantum computer named the Origin Wukong. Yes, named after the legendary Monkey King. According to their official data, this isn't just a lab curiosity. It's a commercially available service. This single machine has provided quantum computing cloud services to over 23 million users from a staggering 139 countries around the world. successfully completing more than 350,000 quantum computing tasks. Let that sink in. 23 million users, 139 countries, hundreds of thousands of tasks completed. This isn't the future. This is happening now. Quantum computers, while still early stage, have demonstrably transitioned from purely theoretical concepts and laboratory experiments to devices that are accessible and performing real computations for people around the globe, albeit through cloud services. And just so you know, this isn't only happening at Origin Quantum. Overseas companies like IBM and D-Wave also offer similar quantum cloud services, proving this isn't an isolated incident, but a real technological shift taking place. Okay, so, if these machines are real and accessible even if through the cloud, who exactly are the primary users of these early quantum computing services? Are they just quantum physicists messing around? Well, yes, some are, but the primary users, the ones actually running tasks, are often researchers in fields that might surprise you, but make perfect sense when you understand what quantum computers are good at. We're talking about areas like computational fluid dynamics, simulating how liquids and gases flow; finance, complex risk analysis, portfolio optimization; biomedicine, understanding protein folding, drug interactions; and pharmaceuticals, designing new molecules. What do all these fields share? They involve finding optimal solutions within incredibly complex mathematical systems. Think of trying to find the perfect shape for an airplane wing to minimize drag, or discovering the absolute best combination of stocks to maximize returns while minimizing risk, or identifying the ideal molecular structure for a life-saving drug. These are problems where the number of possible solutions is astronomically large, and finding the best one using classical computers can take prohibitively long, sometimes centuries. This is precisely the kind of problem quantum computers are inherently suited for. And wouldn't you know it, the training and fine-tuning of large language models falls squarely into this category. Let's break that down for a second. What's the difference between training and fine-tuning in LLM? Training is building the entire model from scratch, like constructing a massive, intricate building from the ground up. You're teaching it everything from basic grammar to complex reasoning patterns. Fine-tuning, on the other hand, is like taking that existing building and renovating a specific wing or redecorating certain rooms to make it perform better for a particular purpose. Maybe you fine-tune a general language model on medical texts to make it an expert medical assistant, or on legal documents to make it a legal aid. At their core, both training and fine-tuning involve a similar underlying mathematical challenge: searching for the minimum point of what's called a loss function in a staggeringly high-dimensional mathematical space. Imagine a landscape with millions, even billions, of hills and valleys. The loss function is the altitude of that landscape. You want to find the absolute lowest point, the deepest valley, because that represents the state where your model is performing optimally, minimizing its loss or error. This search process is often analogized to finding the shortest path through a massive, multi-dimensional maze. Although the specific mechanisms differ significantly, the underlying principle, finding the best solution in a complex space of possibilities, aligns perfectly with the types of problems quantum computers are designed to tackle. So, with this understanding, a crucial question looms. If quantum computers are so good at these kinds of optimization problems, what exactly can they contribute to the world of AI large language models? And why haven't we heard about them revolutionizing AI training rooms before this Origin Quantum announcement? We often hear whispers about quantum computers achieving astonishing breakthroughs, supposedly outperforming classical computers by centuries in certain theoretical tasks. Yet, their practical impact on the actual training and fine-tuning of everyday large language models has, until now, been minimal to non-existent. This gap, this disconnect between the theoretical power and the real-world application in AI, can be attributed to two main factors that have been significant hurdles. First, the current hardware capabilities of quantum computers are still, relatively speaking, in their infancy. When we talk about quantum hardware, we're talking about the number of qubits, the quantum equivalent of bits, but far more powerful, their fidelity, how accurate they are, and their error rates, how often they mess up. Think of building a skyscraper. Current quantum computers are like having only a few dozen high-precision tools that are incredibly sensitive and prone to making mistakes if you breathe on them wrong. This limited number of qubits, coupled with significant noise and errors, severely restricts the complexity of the problems they can handle effectively. They simply don't have enough reliable workers to tackle the massive computational edifice that is a large language model training from scratch. This hardware limitation has been the primary bottleneck preventing them from fully leveraging their potential in large language model applications. Second, while quantum computers, as a theoretical model of computation similar to Turing machines, which represent classical computers, can theoretically solve any problem that classical computers can, their overwhelming advantages, those talked about, speed-ups, are highly dependent on the structure of the problem at hand. In simpler terms, they aren't general-purpose speed demons for everything. They can significantly accelerate the solution of specific problems for which we have developed specialized quantum algorithms that exploit their unique properties. But their effectiveness in handling the wide variety of tasks involved in something as complex as LLM training, let alone achieving that promised acceleration, relies heavily on the availability of mature, well-developed quantum algorithms, specifically designed for these tasks. Since quantum computers perform calculations not through traditional arithmetic, but through the precise manipulation of quantum states using quantum gates composed of qubits. Think of these gates as the fundamental operations. Algorithm design is absolutely critical. It's like needing a specific dance routine, the algorithm, to make the quantum dancers, the qubits, perform the right steps. Currently, the practical versatility and widespread application of quantum computers are largely constrained by the scarcity and immaturity of these specialized algorithms. Our understanding and utilization of them, especially for complex tasks like AI model optimization, remain frustratingly in their infancy. So, for now, when it comes to tackling large language models, the most viable and practical strategy isn't a purely quantum approach. It's a hybrid approach, cleverly combining the strengths of classical and quantum computing. The overall process still operates predominantly within the familiar framework of classical computing, using powerful GPUs and CPUs for the bulk of the work. But quantum computers are brought in as specialized co-processors, utilized to handle specific, computationally intensive components, where they do show potential advantage. This often involves tasks that can be framed as combinatorial optimization problems in high-dimensional mathematical spaces, exactly the type of problem we identified earlier. The recent achievement by Origin Quantum is a perfect illustration of this hybrid approach in action. It demonstrates that quantum computers can indeed play a valuable role in this specific context, handling a targeted optimization task within the larger framework of LLM development. It's crucially important to note, as the article points out, that current quantum computers absolutely cannot complete the entire training process of a massive large language model from scratch. They are only capable at this stage of handling specific parts, like the fine-tuning process. Why only fine-tuning? Because fine-tuning focuses on optimizing specific subsets of parameters or adapting the model on a more limited dataset. This task, while still complex, is significantly less computationally demanding than full training and can be tackled using current quantum computers like the Origin Wukong, which, while impressive, has around 70-something qubits. To train a truly large language model from scratch, you would likely require thousands, perhaps even millions, of stable, high-fidelity qubits, a capability that is still years, if not decades, away. So while this breakthrough by Origin Quantum is incredibly exciting and validates the technical feasibility of using quantum computers for some aspects of large language model optimization, specifically fine-tuning, it absolutely does not mean that quantum computers are ready to sweep in and dominate the large language model market tomorrow. Classical computers powered by GPUs are still firmly in the driver's seat for the vast majority of AI workloads. Nevertheless, this achievement represents a genuinely significant step forward. It's proof of concept. It opens up new, tantalizing possibilities for the future at the intersection of AI and quantum computing. It shows that the theoretical potential isn't just theoretical anymore. It can translate into real-world results, even on today's early-stage quantum hardware. However, we must be clear-eyed. The current quantum computing devices available today are still in a rather rudimentary stage. They are noisy, error-prone, and difficult to scale. A major reason for this is that quantum computers are currently grappling with the immense challenge of error correction. Qubits are incredibly sensitive to their environment, and even the slightest disturbance can cause errors that cascade through a computation. Building fault-tolerant quantum computers with robust error correction is one of the biggest engineering hurdles facing the field. Despite these challenges, the successful fine-tuning of a large language model with 1 billion parameters using a quantum computer is, in itself, a groundbreaking achievement. It has, at the very least, definitively demonstrated that, although quantum computing is still in its infancy, it can already make tangible inroads into the popular, commercially relevant fields dominated by classical computing and achieve remarkable, quantifiable results like parameter reduction and effectiveness increase. This brings us to a deeper, more intriguing question. As quantum computing technology matures, and we potentially move towards using them for more complex tasks, perhaps even parts of the full training process in the future, what unique, fundamental advantages do they inherently possess compared to classical computers, especially the powerful ones equipped with cutting-edge GPU technology? To answer this, we need to understand a key characteristic that fundamentally differentiates quantum computers from everything you're using right now. While quantum computers have elements like qubits and quantum gates that have loose counterparts in classical computing, bits and logic gates, their computational process is not based on performing simple arithmetic operations like addition, subtraction, multiplication, and division in a binary system using zeros and ones. Instead, it's a physical evolution process governed by specific quantum algorithms, where the quantum states of the qubits are manipulated according to the rules of quantum mechanics. In this process, there are three crucial concepts from quantums, mechanics that empower quantum computers and give them their potential edge. Concepts we need to familiarize ourselves with: superposition, entanglement, and interference. First, let's talk about superposition. In classical computing, a bit is like a light switch. It's either definitely 0 or definitely 1 at any given time. Simple, clear-cut. But in quantum computing, a qubit is like a light dimmer that can be set to both 0 and 1 simultaneously, existing in a state that's a combination of both possibilities, each with a certain probability amplitude. This is the state of superposition. Why is this powerful? Because if you have just n qubits, due to superposition, they can simultaneously represent a combination of two different classical states. 2 qubits can represent 0, 0, 0, 1, 10, and 11 all at once. 3 qubits can represent 2, 3, for 8 states simultaneously, and so on. This exponential growth in representable states is a direct manifestation of quantum parallelism. It's not that the quantum computer is performing 2n calculations simultaneously in the classical sense, but rather that the computation is acting on a superposition of 2n inputs or possibilities at the same time. This is where the analogy of searching for treasures in a mountain area comes in. Classical computing is like systematically searching the mountain area one region at a time, checking every potential spot sequentially or in parallel on different classical processors, but still fundamentally scanning discrete locations. While quantum computing, thanks to superposition, is potentially like having an aerial view of the entire mountain from a drone, simultaneously assessing the potential of many locations at once based on some overarching property, and then homing in on the most promising areas. This potential to explore a vast number of possibilities simultaneously is the immense value of the parallelism brought about by the superposition state, especially for tasks like the fine-tuning or optimization within large language models, where you're searching for the best combination of parameters out of a massive space. Theoretically, this could significantly accelerate the search process without consuming a large amount of electrical power compared to adding more and more classical processors. Moreover, as the number of stable, high-fidelity qubits increases, the gap in this ability to accelerate the search process between quantum computing and classical computing is predicted to become even more pronounced, which is often cited as the most significant potential advantage of quantum computing compared to traditional GPU-based solutions for certain problems. Evidently, due to these characteristics, quantum computing holds the promise of alleviating the anxiety about computing power to a large extent for specific tasks. Next, let's consider entanglement. Of course, this refers to quantum entanglement, perhaps the most mind-bending aspect of quantum mechanics that Einstein famously called spooky action at a distance. In a quantum computer, multiple qubits can be set to an entangled state. Physically, entanglement is defined as the situation where, after multiple particles become entangled, the state of a single particle can no longer be described independently of the others. They are intrinsically linked. And perhaps most counterintuitively, any change or measurement on one entangled particle will instantaneously influence the state of the other entangled particles, regardless of the physical distance between them. This characteristic creates powerful, non-local correlations between qubits. It's like having a set of interconnected gears, where turning one instantly and predictably affects the state of all the others, no matter how they are arranged. This intricate, non-local connectivity is what enables the design of some complex multi-qubit logic gates that are essential for quantum algorithms. Some people may wonder about the entanglement state in the context of large language models. As mentioned earlier, entanglement represents complex, non-local correlations between qubits. A large language model, at its heart, is essentially a complex collection of parameters, the weights and biases of the neural network, and these parameters have incredibly complex, long-range dependencies because it is a neural network with multiple interconnected layers, and there are numerous weight connections not only within each layer, but also between layers. So can the entanglement characteristic of quantum computers be naturally mapped onto the long-range correlations and dependencies of the neural network structure in an LLM? Theoretically, it feels like there should be a natural fit, a way to leverage this inherent quantum connectivity to represent the intricate relationships within the neural network. However, currently, this direct, seamless mapping cannot be fully achieved or exploited in a practical sense, primarily because the number of high-quality qubits required to represent the complex entanglement needed for a massive LLM's parameters far exceeds what current devices can provide. At present, in the field of quantum computing, the main approach to realizing and leveraging some of these complex weight dependencies in a structure suitable for tasks like LLM fine-tuning is through the concept of quantum neural networks, QNNs. This is the solution structure adopted by projects like the Origin Wukong implementation. A quantum neural network is, in essence, a structure that attempts to simulate or adapt the neural network architecture from classical computing, but built upon the different hierarchical components unique to quantum computing, such as qubits, quantum gates, and quantum circuits. Although the entanglement characteristic is often abundant within the quantum circuits that make up quantum neural networks, it mainly serves as a fundamental resource for constructing the necessary quantum gates and enabling the quantum computation itself, rather than directly representing a one-to-one mapping of a classical neural network's specific weight dependencies. Through the meticulous design and arrangement of these quantum gates, which operate on the entangled states of qubits, non-linear characteristics, essential for learning and optimization, can be introduced for parameter updates, similar to the role of activation functions in classical neural networks. It is important to emphasize that in a quantum neural network, the entanglement state, as a core quantum resource, actually enhances the expressive power of the quantum circuit. Theoretically, this means a relatively small quantum circuit utilizing entanglement can represent and explore high-dimensional nonlinear relationships and correlations that are difficult, perhaps even impossible, to efficiently simulate or discover using classical computing alone. Finally, let's touch upon interference. The essence of interference in quantum computing is a means of driving the dynamic evolution of the quantum computer system towards a desired outcome. To understand this, it's important to reiterate that a quantum computer isn't truly calculating, in the traditional sense of performing arithmetic steps. Instead, it uses specific quantum algorithms to manipulate the superposition and entanglement of qubits, guiding the entire system's probability distribution towards a state that encodes the optimal solution. Since a qubit is in a superposition of 0 and 1 with each having its own probability amplitude, a complex number related to the likelihood of measuring 0 or 1, the computation process is essentially a dynamic change of these amplitudes, influenced by the quantum gates. Interference, in the quantum sense, like wave interference where peaks reinforce and troughs cancel, is used constructively to amplify the probability amplitudes associated with the correct or desired outcomes, like the optimal parameter combination, and destructively to cancel out the amplitudes associated with incorrect or undesirable outcomes. Eventually, through a measurement at the end of the computation, the superposition collapses, and a string of binary codes, zeros and ones, is obtained, corresponding to one of the possible outcomes with a probability determined by its final amplitude. Due to the probabilistic nature and the presence of error rates in current devices, multiple measurements are typically required to obtain a probability distribution over the possible outcomes, from which the most likely or desired result is inferred. This probabilistic nature and the reliance on measuring probability distributions is a fundamental difference between quantum computing and classical computing. Based on these fascinating characteristics, superposition, entanglement, and interference, quantum computers possess potential unique advantages in the field of large language models, particularly for optimization tasks like fine-tuning. Why is this so? The superposition state implies that it can represent and effectively explore two Darwin states simultaneously, allowing it to evaluate the potential quality of a vast number of optimal combinations of multiple parameters at the same time. Remember, the drone analogy? It's about seeing and assessing the whole landscape of possibilities broadly. This is the value of the parallelism brought about by the superposition state for tasks such as the fine-tuning of large language models. Theoretically, it can significantly accelerate the search process for optimal parameters without necessarily consuming a large amount of electricity compared to brute forcing or extensively searching the space classically. Moreover, as the number of qubits increases, the gap in this acceleration ability between quantum computing and classical computing is expected to become even more pronounced, which is arguably the most significant potential advantage of quantum computing compared to traditional GPU-based solutions for these types of problems. Evidently, due to these characteristics, quantum computing holds the potential to alleviate the anxiety about computing power and its associated costs and energy consumption to a large extent for specific, suitable problems within AI. The combination of entanglement, enhancing expressive power, and the nonlinear transformations enabled by quantum gates within a quantum neural network allows the quantum system to explore the parameter space in ways that are fundamentally different from classical optimization methods. Think back to our mountain landscape analogy for the loss function. Classical methods, like gradient descent used heavily in AI, are often like a hiker carefully finding their way downhill by always taking the steepest path in their immediate vicinity. This works well, but they can get stuck in local minima, valleys that aren't the absolute lowest point on the entire landscape. Theoretically, through superposition, exploring many points at once, entanglement, connecting different parts of the search space in non-local ways, and the nonlinear transformation of quantum gates, quantum computers have a high probability of uncovering optimization patterns or finding lower minima that are difficult or even impossible to discover efficiently using classical algorithms. This allows them to see and capture areas or relationships that are difficult for classical computing to cover or exploit. Therefore, this gives quantum computing significant potential advantages in the lightweighting of large language models. Lightweighting is the process of making models smaller and more efficient, e.g., pruning unnecessary connections, quantizing parameters to lower precision, so they can run faster and on less powerful hardware. Quantum computing, leveraging its unique capabilities, may be able to explore higher performance parameter combinations, or even reveal more efficient underlying network structures, which are simply beyond the reach of classical lightweighting solutions like pruning and quantization. The Origin quantum achievement, with its reported 76% reduction in effective parameters while increasing effectiveness, has already preliminarily demonstrated such capabilities for quantum computing in the context of fine-tuning. It suggests quantum methods might find more optimal, sparser, or lower precision representations that classical methods struggle to identify. This achievement by Origin Quantum should absolutely be regarded as a moment worthy of record, a marker point in history. Previously, the practical impact and achievements of quantum computing, while significant scientifically, have mainly focused on fields such as materials science, finance, and medicine, areas that, while important, still feel relatively distant from the daily lives of ordinary people. However, large language models have now burst into the mainstream consciousness. They have become a very common internet application that has had a significant and tangible impact on how ordinary people access information, create content, and interact with technology. If quantum computers can indeed play a crucial role in the training and fine-tuning of large language models, even if initially only in specific powerful ways like optimization and lightweighting, their existence is highly likely to accelerate the evolution of large language models, potentially making high performance, more efficient, and perhaps even entirely new types of large language models accessible to everyone, running on devices or infrastructure that is currently unimaginable, especially in the current situation where access to cutting-edge GPUs presents significant ecological barriers, dominated by a few players. The cost of purchasing or renting the necessary computing power remains prohibitively high for many, and the energy consumption for training these models is truly astonishing, a major environmental concern. Quantum computers, focusing on specific tasks where they offer inherent advantages, may be able to provide truly disruptive solutions to some of these pressing problems, not by replacing classical computers entirely, but by acting as powerful, specialized accelerators that change the game for AI development. So, what's the takeaway from this fascinating intersection of quantum physics and artificial intelligence? For me, the lesson is one of patience, persistence, and the unexpected places breakthroughs can occur. We often want revolutionary technology to arrive fully formed and immediately displace everything that came before it. But real progress, especially with something as fundamentally different as quantum computing, is messy, incremental, and often involves hybrid approaches. This achievement shows that even in their rudimentary stage, These quantum machines are capable of doing things classical computers struggle with, and those capabilities can have a direct impact on the AI tools we use every day. It reminds us that the biggest challenges, like the computational demands of AI or the limitations of current hardware, often require looking outside the box, combining different fields, and patiently working through the immense engineering and theoretical hurdles. It's a testament to human curiosity and ingenuity, pushing the boundaries of what's possible, qubit by qubit, algorithm by algorithm. It makes you wonder, doesn't it? What other seemingly unrelated scientific fields hold the key to unlocking the next level for technologies we already rely on? How will your interaction with AI change when quantum computers start to truly leave their mark? Stay curious, stay healthy, and keep exploring the amazing world of science and technology with us. And if you found this journey into the quantum future of AI as exciting as I did, please consider hitting that subscribe button. It helps us keep exploring these fascinating topics together.